Hello gems! Welcome to A series. In this video, we are going to discuss previous year BITSAT questions from the chapter of electric charges and fields. Okay, so the discussion over here is very smooth. We are going to start with the super easy category questions first, and then we'll eventually move to the toughest question of the day. Okay, so I've tried my best to make every question in this video crystal clear. Also, if you have missed the previous videos of A series, you can go check out the description box below. Without a further ado, let's begin today's class. So question 1 and 2 over here from the super easy category. In question 1 from 2009, you have an electron which is moving in an electric field. The direction of the electric field is as shown. Okay, the direction of the initial velocity vector is as shown. Now you can see that the initial velocity vector makes an angle theta with the electric field. Okay, you are supposed to predict the path of this electron. Okay, very simple question. You can see that this electron, the force on this electron will be opposite to the direction of the electric field. The answer over here is D, parabola. Okay, the path of that electron will be parabolic, or it will describe a parabola. Okay, so you can see that force on this electron will be opposite to the direction of field. Okay, because force is nothing but minus, in case of electron it will be minus E, right? Charge on electron minus E into the electric field. Okay, so you can see that force is opposite to the electric field. Okay, now initial velocity vector is in this direction, so I can call the direction of force as direction of acceleration. And I remember I told you that about this in motion in 2 dimension, that when acceleration and velocity vector make an oblique angle with each other. By oblique I mean an angle which is not equal to 0 degree and not equal to 180 degree. An angle wherein they are both of them are not parallel or anti-parallel. Okay, some oblique angle between them. You can see this alpha is not equal to 180 degree or 0 degree. Okay, so when the acceleration and initial velocity vector make an oblique angle with each other, the path is parabolic. Okay, I mentioned this in motion in 2 dimensions. Okay, in the very introductory lecture. Now, so here the path of this electron will be nothing but a parabola. Okay, so parabola D is the correct answer. Now coming to question 2. In question 2, you have 2 charges Q1 and Q2. The force on one due to 2 is given as F. Now you bring one more charge Q3 over there. You are asked for the same quantity. You are supposed to comment on the same quantity, force on 1 due to 2. What will happen to that quantity? Will it decrease, increase, remain same, or will it depend on the size, on the sign of Q3? Okay, quite a simple question. It is based on your superposition theorem, or to be precise, it is based on the next line of superposition theorem. Your superposition theorem states that the net force on n charge is given by the vector sum of the forces by other charges taken one at a time. Okay, but that is not what we are going to use over here. The line that we are going to use is that the force between any two charges, is independent of the presence of the third charge. Okay, so force between 1 and 2 is independent. It does not depend on the presence of Q3, which means that force over here and here is the same, since it does not depend on the presence or absence of Q3. Just like gravitational force, if I have 2 things over here, this calculator and this pen, the gravitational force between them suppose is F. Now I bring myself between these 2 things, again the gravitational force between them is F. Okay, so same thing applies over here. The force between the force of interaction between Q1 and Q2 is independent of the presence of Q3. Okay, so interaction among them is independent, which means that the force will remain same in both the cases. So C, option C, remain same is the correct choice over here. Let's move to the next question now. So question 3 and 4 over here. In question 3 from 2011, you are asked for the correct plot of E versus R graph for a solid non-conducting sphere of radius R. Okay, quite a simple one again, because we know that inside a solid non-conducting sphere, okay, inside a solid non-conducting sphere, the field is directly proportional to R. Okay, or you can say that for distances smaller than the radius inside the sphere, there is a direct relationship between the field and the distance. Okay, so option A is incorrect and option B is incorrect, since you cannot see a linear relationship over there. However, option C and option D, the relationship is linear, right, in the region inside. Okay, for distances smaller than r, the relationship is linear, it is a straight line. Okay, directly proportional over here. Okay, so either option C or option D is correct. Now let's analyze what happens when we go outside the solid conducting sphere. We know that outside a solid conducting sphere, the field is like any other sphere, inversely proportional to 1 by r square, right, inversely proportional to the distance square. So which is the graph showing that? Option C, right, inversely proportional to the distance square. Here the field outside, of course, does not become 0 suddenly, it is inversely proportional to r square. So option C is the correct choice over here. Let's move to question 4 now. Again, a simple question. In this question, you are given a dipole. Okay, you are supposed to find the ratio of electric field at axial point to electric field at equatorial point. Okay, for equal distances, of course. So you'll know that electric field at axial point, okay, you have to take the magnitude. Okay, now electric field at axial point is given as 2 kp by r cube, right, and electric field at equatorial point is given as kp by r cube or minus kp by r cube, but anyways we just want the magnitude, right? So when you take the ratio, you can simply see that it will be 2:1, right, 2:1. So this kp by r cube will get cancelled and the ratio that you will get is 2:1. So option B, 2:1, 2:1 is the correct choice over here. Next question. Now question 5 over here, you can note that we have increased the level now. It is a question from the easy category. Okay, so in this question you have an equilateral triangle. At the vertices of this equilateral triangle, you have placed 3 identical charges, plus q, plus q, plus q. You are supposed to find the electrical field at this point O. Okay, it is a very simple question. You can directly see it through symmetry that the electric field at this point O will be nothing but 0. Okay, I'll just give you a feel for it. I'll also tell you the approach to prove it. You can go ahead and prove it. Okay, anyways, you can see it through symmetry that the electric field at this point will be 0. Okay, I'll show you. Now electric field due to this charge q at this point will be in the outward direction, right? So let's call it E. The magnitude of this E will be nothing but kq by a square, right, at a distance A. Now due to this q, again it will be E, right, but just in the magnitude will be E, again kq by a square, right, and the direction will be something different. Now due to this q, the electric field will be again E, magnitude wise it will be the same, kq by a square, and the direction will be like this, right? Now you can feel it that these two fields, okay, the resultant of these two fields due to this charge and due to this charge will be in this direction, right, along this line, and this field ER will be nothing but equal to E, and this E and this E will get cancelled. Okay, you can actually go ahead and prove this. I'll tell you the angle between this two E, these two electric fields. Angle between these two electric fields is 120 degree. Okay, I can prove that too. This angle is 60 degrees since it's an equilateral triangle. Here the angle is 30 degree. I can drop this perpendicular. So here the angle will be 60 degree, right? Angle sum property 90, 30, 60. Okay, this is 60, this is 60. And you can see that this and this are vertically opposite angles, right? This and this are vertically opposite angles. So since here it is 120, the angle between these two electric fields will be 120 degree. Okay, so you can find the resultant of these two electric fields and it will come out equal to E. Okay, you find that the resultant will come out equal to E. You can use your vector logics and it will bisect this angle, right? So yeah, it will bisect this angle and this E resultant, which is nothing but E, will cancel with that. Okay, actually you can directly see it through symmetry. Symmetry holds for other polygons also. You can have a square with like charges at its vertices, plus q, plus q, plus q, everywhere, right? And if you are asked for the field at the center where the two diagonals meet, again the field over there will be 0. Okay, so you can apply the symmetry logics to any polygon. Here we applied it to equilateral triangle. Okay, anyways, we'll move to the next question now. So question 6 over here. Here again in this question you can see an equilateral triangle, okay, with the three identical charges plus q plus q plus q at its vertices. I was stupid enough to erase off the previous question and redraw this again. Okay, anyways, you are asked for force on any charge. Okay, you pick any charge among this and find the force on it. No need to worry, force on each of this will be the same due to symmetry. Okay, so let's pick this one as 3. Okay, let's say this one is 2, this one is 1. Okay, so we are going to pick the third one. We are going to find the force on third one. Okay, so the approach is quite simple. First of all, use your superposition theorem. So the force on the third one will be the vector sum of the force on the third one due to the first one. I'll write it. Force on third one will be the vector sum of forces of force on third due to the first plus force on third due to the second. Okay, I just applied the superposition theorem. Now you can see that force on third due to the first one will be in this direction, right? It will repel, plus q, it will repel, and the force will be in this direction. Okay, and now the force on the third one due to the second one will be along this line, right? Again they will repel, plus q. Okay, also you can note that the magnitude of these two forces will be equal, which will be equal to kq square in either of the case, kq square by the distance is again the same, a square, right? So the magnitude is same in both the cases, just the direction is different. Okay, in the case in the first one the direction is along this line, in the second one the direction is along this line. Now you can see that the angle between these two is nothing but 60 degree, right? If you see, this is an equilateral triangle. Here the angle will be 60 degree. So here they are vertically opposite angles, right? This and this. So this will be 60 degree as well. So now just apply your vector logics. Here you just want the magnitude, right? So how to find the magnitude? Here you have f and f. Okay, how to find the magnitude of two vectors? It is given as, so the resultant force, which is the force on 3, will be given as, the magnitude will be given as a square, which is f square, plus b square, which is again f square, plus 2ab, so 2f square into cos theta, right? Cos 60, so cos 60 will be half. I can directly substitute that. So this and this will get cancelled and you'll get root 3 f square, and f square will come out of the root sign as f. Okay, so root 3f, and f is nothing but, we already wrote it over here, it is kq square by a square. Okay, so the net force on the third one, or any of the charge for that case will be root 3 kq square by a square. Root 3 kq square by a square. Just write this properly. Okay, root 3 kq square by a square. Option B is the correct choice. Next question. So question 7 over here. In this question you have two spheres, sphere A and sphere B. The radius of sphere A is r, the radius of sphere B is 2r. Okay, a charge capital Q is distributed among these two such that their charge densities become same. Okay, a charge capital Q is distributed among sphere A and B, so such that their charge densities become equal. You are supposed to find the charge on the bigger sphere. Find the charge on this one, the sphere B, bigger sphere. Okay, so the approach is straightforward over here. Okay, we are going to exploit this data, right? Their charge densities become same. So when their charge densities become same, we can simply write sigma A equals sigma B. Okay, charge density of A equals charge density of B. So charge density of A can be written as charge on A divided by 4 pi r a square. The radius of A is simply r, right? So I can write it as 4 pi r square, and here I can write sigma B as charge on B divided by 4 pi rb square. What is the radius of B? It is 2r, right? So I can write it as 2r square. Okay, Now I will use charge conservation over here. Let's suppose that the charge on the bigger one, let's write it as QB. Okay, the charge on B is Q big is nothing but QB. Okay, we have considered that over here. Now can we express this QA in terms of QB? We can. Okay, you can see that this charge Q was distributed among these two, right? This charge Q, I can write Q as QA plus QB, right? This charge Q was distributed among these two, so I can write Q equals QA plus QB, and I can write this QA, I can write this QA as Q minus QB. Okay, I hope that is clear. This charge Q was distributed among these two, so I can write Q, this capital Q equals QA, charge on A plus charge on B. Okay, now I want to write QA in terms of QB, so I brought this QB to the other side. So QA is nothing but capital Q, the initial charge which was distributed, minus the charge given to B. Quite logical if you see. Okay, so here I'll plug in that value and we'll get our answer. First of all, this 4 pi and 4 pi will get cancelled. R square will cancel with that R square. QA is nothing but a Q minus QB. Okay, and here you'll get QB by 2 square, which is 4. Okay, so you cross multiply this. 4QB will give you QB. Now we have to find this QB, so 4Q will give you, take it to the other side, that will give you 5QB, right? So 4Q by 5 equals QB, and this is the thing that we want, right? The charge on the bigger one, QB. Okay, so the answer is 4Q by 5. Option A is the correct choice over here. We just exploited the data that was given in the question, which is charge density of both the spheres is equal. Okay, so we just exploited that data, some wise manipulation using conservation of charge, and then we reached our answer. Okay, over to the next question. So again in question 8 you have two spheres, and as usual I erased off the spheres in the previous question and redrew it again. Yeah, thank you. So in this question the radius of this sphere is 1 centimeter, the radius of this sphere is 3 centimeter. Okay, charge on this one is given, charge on this one is given. Now you are going to connect this two spheres with a conducting wire. Of course some amount of charge is going to flow between these two spheres. Okay, some amount of charge is going to exchange between these two spheres, and the final charge on this sphere of 1 centimeter is small q, and the final charge on that sphere with radius 3 centimeter is capital Q. Okay, you are supposed to find this capital Q. Okay, it is a conceptual one. If you know the concept, you will be able to do it. First of all, tell me, why does the charge flow? Okay, what is the reason for the flow of charge? It is simply a difference in potential, right? There is difference in potential between these two spheres, and that's why the charge flow. And now when will the charge stop flowing? Simple again, when the potential of both the spheres are equal. Okay, when the potentials of both the sphere are equal, there will be no difference in potential and the charge will stop flowing. Okay, so the concept is to equate the potential of the two spheres. Okay, when the potential is equal, the charge will stop flowing. Okay, and this will be the condition. The charge over here will be Q and the charge over here will be capital Q. Okay, so here you can see I'll call this as sphere A and this as sphere B. Okay, so when the potential of sphere A equals potential of sphere B, this condition will be obtained. Okay, charge on this one will be small q, charge on that one will be capital Q. Now you can write this potential as kq by r, right? Okay, so we can write this potential as k charge on the sphere, which is small q, and the radius of the sphere 1 centimeter. Okay, I'll keep it in centimeters, it's just going to cancel over there. Okay, and here we can write potential of B as k charge on this sphere, charge on the sphere B, which is capital Q, divided by its radius, which is 3 centimeter. Okay, now this k and this k will get cancelled, and you'll get a relation between q and small q. Okay, q equals 3 times small q. Now how will you find this small q? Okay, you have to just express the small q in terms of this. Okay, again we are going to use conservation of charge. Okay, charge cannot be created and destroyed in this journey, right? From here to here, no charge is created, no charge is destroyed. Okay, so initial charge, the sum of these two charge should be equal to sum of these two charges, right? So just add these two charges and that will give you -1 into 10 to the power -2 and 5 into 10 to the power -2. 5 minus 1, that will be 4. So this is the total charge in the initial condition, 5 minus 4 into 10 to the power -2, and that will be equal to Q plus Q, right? Simple conservation of charge. Okay, so from here you can write the value of this. Now we want the value of big Q, right? So let's substitute for small q. So small q will be given as 4 into 10 to the power -2 minus this capital Q. Okay, just substitute that over here. So you'll get 3 into 3 4s are 12. I'll directly do it. 12 into 10 to the power -2 into, sorry, minus 3 times that one. So 3q. So 4q will be equal to 12 into 10 to the power -2, and q will be nothing but 3 into 10 to the power -2 coulombs, right? And this will be the correct answer. 3 into 10 to the power -2. Option B is the correct choice over here. Okay, so the only concept over here was potential of A equals potential at B and some logic of conservation of charge. Okay, over to the next question. Now question 9 over here. In this question, a cavity is made in this conductor. Okay, a point charge plus Q is placed at the center of this cavity. Regions are marked as 1, 2 and 3. Region 1 represents the inner surface of the cavity. Region 2 represents the outer surface of your conductor, and region 3 is the region between them. Okay, so you are supposed to find the charge at 1, 2 and 3 respectively. Find the charge at 1, 2 and 3 respectively. Here are your options. You can give this question a humble try. It is a conceptual one. It is a good one. Okay, so the first step is to draw a Gaussian surface over here. Okay, why are we drawing Gaussian surface? I'll tell you why. Okay, so here you can see that this cavity, first of all, you can see that this cavity is inside this conductor, right? And we know that electric field inside a conductor is 0. Okay, there should be no electric field inside this conductor. Okay, so I can say that flux through this Gaussian surface that I have drawn should be 0, because there is no electric field, right? No electric field inside the conductor, which means no field lines, of course, right? So the flux in this region, in the Gaussian surface that I have drawn, should be 0. So basically I can say charge enclosed by epsilon naught should be 0 by Gauss law, right? Flux is nothing but charge enclosed by epsilon naught. Okay, so here, from here I can conclude that the charge enclosed should be 0. Okay, charge enclosed by this Gaussian surface should be 0. Okay, but you can see that the charge enclosed by this surface is plus q. So what will happen is that a charge minus q will be induced on the inner surface of your cavity. Okay, just to cancel this electric field due to this point charge. Okay, minus q charge will be uniformly distributed on the inner surface of the cavity, and that will kill the field due to this point charge, and hence the flux will be 0 and the charge enclosed plus q, and this is minus q, right? Plus q minus q, 0. Charge enclosed will be 0. Okay, so you can see that the charge on the inner surface here, it should be minus q. Of course, now the charge between them will be 0, right? There should be no charge here in the material, because electric field inside the material is 0, right? Electric field inside the conductor is 0. Okay, so there should be no charge in the region 3. So minus q, yeah, only one option we have, minus q plus q, 0. Okay, let's prove this as plus q. Now why will be this plus q? Because the option suggests no. Let's see how. Okay, so first of all, you can see that the conductor was neutral, right? And a minus q charge was induced over it. Okay, minus q was induced on the inner surface of the cavity, and that is a part of the conductor. So in order to maintain its neutrality, a plus q charge will be developed on the surface. Okay, it will be uniformly distributed as well. So you can say that the charge on the outer surface of the conductor is plus q. Okay, this minus q, now let's sum it up. This minus q is to cancel the field due to this point charge. Okay, this will cancel this field and the flux will be 0, and you can see plus q minus q. Add this to the charge enclosed in this region will be 0, right? So the flux will be 0. Okay, now in order to maintain electrical neutrality, charge plus q will be induced on the outer surface, because minus q was induced on the inner surface of the cavity, right? So plus q will be induced on the outer surface. So plus q plus minus q will give you 0, which is neutral, right? So this charge plus q is developed to maintain neutrality. Okay, so where is that developed? That is developed on the outer surface of your conductor, okay, which is region 2. So minus q plus q 0, minus q plus q 0, option C is the correct choice over here. Okay, it was a conceptual one. You can surely note it down. The notes are available on the website too. Let's move to the next question now. So question 10 over here from 2006. In this question you have a charge q which is placed at the upper surface of your cylindrical vessel. You are supposed to find the flux through this vessel. Okay, it's slight tricky if you see, because this charge q is not enclosed inside the vessel, right? It's there on the surface, it is not enclosed. Okay, so you cannot apply your Gauss law directly. You have to use some logic, some approach here and there. Okay, so I'll give you an approach in this question, and this approach will be tested in the next question. Okay, so pay attention over here. So what I will do first is I'll just try to complete this figure. Okay, by completing this figure I just mean I just want to enclose that charge q. Okay, so I'll draw one more cylinder on top of this. Okay, just an imaginary one. I'll assume it's there now. Okay, so I have drawn this cylinder now. So if we consider that cylinder, you can see that the charge q is now enclosed. Okay, now the flux through this cylinder, this entire cylinder, considering that imaginary cylinder as well, the flux through this entire system will be equal to, the flux will be equal to charge enclosed. Now this q is enclosed, right? This q is enclosed in that system, so q divided by epsilon naught. But we want flux through this vessel, right? We don't want flux through this system. We are just going to ignore this one. Okay, so you can see that now you have to use symmetry logics. Okay, you can see that due to symmetry, half of the flux will be on this side and half of the flux will be on this side. Okay, half of the flux will pass through this one. Okay, it's symmetric, right? So half of the flux passes through the vessel and half of the flux passes through the cylinder that we have imagined. Okay, you can see it as half of the hemisphere of the flux will be on top, okay, which passes through the imaginary cylinder that we have considered, and half of the hemispherical flux. Okay, I'm just referring to it in a very lame way. Okay, don't take it seriously. Okay, so half of the hemispherical flux is passing through your vessel, right? So half of the total flux is passing through the vessel by symmetry. Okay, half of the flux is passing through the imaginary thing, half of the flux is passing through the vessel. Okay, I hope you can imagine that. So the flux through the vessel will be nothing but half of this, right? Half of this. This is the total flux passing through the system. Half is passing through the imaginary thing, so half is passing through the vessel. So half q by 2 epsilon naught is the correct answer. So option C, q by 2 epsilon naught is the correct answer over here. Okay, so the approach is quite simple. First imagine or complete the figure so as to enclose that charge q. Okay, write the total flux which will be q by epsilon naught, and then look out for symmetry. Okay, you can just look out for among how many figures is that q shared. Okay, among how many objects or figures is that q shared. Okay, you can see that this q is shared among these two figures. Okay, so you can simply refer to as q by 2 epsilon naught, because half of the flux will pass through this one and half of it will pass through the other one. Okay, let's move to the next question now, where this concept will be tested. Question 11 over here, time for test. Let's see how much you have understood the approach that I have taught you in the previous question. Okay, so in this question you have a plate of dimensions LL. A charge Q is placed at a height of L by 2 from the center of this plate. Okay, I hope you can imagine that. Suppose this is the plate of dimensions L and L. A charge Q is placed at a height of L by 2 from this plate, just at the center. Okay, so you have to find the flux through this plate. So you can pause this video and give this question a humble try. Also mention the time of this video and tell me your answer, A, B, C, D. Okay, so you can pause this video now and give this question a try. I'll do it in 3, 2, 1. Okay, so first of all we have to enclose this Q, right? First of all, this Q is not enclosed, and we cannot apply our Gauss law directly. So first step is to enclose this cube. Okay, think of an imaginary figure. So I can think of a cube. Okay, so I'll choose a cube over here of dimension L. Okay, and this plate is nothing but the plate of our consideration. Okay, we have to find the flux through this plate. Okay, so the charge will be at a distance of L by 2, at a height of L by 2 from this plate. So you can see that this charge is at the center of that cube. Okay, so you can see that the flux through this cube will be Q by epsilon naught. Right, flux through this cube will be Q by epsilon naught, right? Charge enclosed, which is Q by epsilon naught. Now we want the flux through the plate. Okay, and the plate is nothing but a face of the cube. How many such faces are there? 6, right? 1, 2, 3, 4, one in the front and one at the back, right? So 6 faces. Okay, so this flux will be divided equally among the 6 faces. Okay, so due to symmetry, of course. So okay, so the flux through the plate will be nothing but 1/6 of this flux. Okay, so Q by 6 epsilon naught. Option C is the correct choice over here. Okay, I'll just explain that in a brief. So first of all, we chose a cube since we want to enclose that charge. Now we found out that the flux through the cube is Q by epsilon naught, charge enclosed by epsilon naught, but we want flux through the plate. Okay, so for that we noticed that the plate was just a face of cube. Now this flux will be symmetrically, due to its symmetry, it's equally divided among the 6 faces. Okay, the upward face, downward face, the 2 faces at the side, and the front face and the back face. Okay, so this flux due to this charge is equally distributed among the 6 faces, and each face, okay, each face will have 1/6 of this total flux, right? So the flux through this plate, which is a face of that cube, is nothing but 1/6 of Q by epsilon naught. And not gonna lie, this is a question from your NCERT. Okay, so this is a question from your NCERT. So study your NCERT properly before you go to attempt your BITSAT questions. Okay, so let's move to the next question now. So question 12 over here. In this question, you are given 2 dipoles with their respective dipole moments. One is at 0, 0, 0 and the other one is at 1, 0, 2. Okay, you are supposed to find the electric field at 1, 0, 0. Okay, due to this 2 dipoles. Might seem complicated, but it is actually very simple. Okay, let's just analyze the scenario over here. We'll draw the XZ plane. Okay, y is 0 in all the 3 cases, 0, 0, 0, right? So let's just consider the XZ plane over here. So you can see that the first dipole over here is at the origin, right? This dipole, the center of this dipole is at the origin, and the direction of this dipole is along the z-axis, right? Along k cap. So this is our first dipole. It has the magnitude of the dipole is p. Okay, now coming to the second dipole, it has a magnitude of p by 2 and it is at a point 1, 2, right? XZ. Just look for XZ. X on the x-axis it's 1 and on the y-axis, on the z-axis it's 2. Okay, so somewhere here we have the center of this dipole. Okay, this dipole has a magnitude of p by 2. The dipole moment's magnitude is p by 2 and the direction is same as this one, which is along the positive z axis, okay, along k cap. Now you have to find the electric field at 1, 0, 0 or 1, 0, 1 on the x-axis and 0 on the z-axis. Okay, so you have to find the electric field at this point. Okay, you have to find electric field at this point. This is 1, 0, 0. Okay, so yeah, so you can see that for this dipole, this is an equatorial point, and for this dipole, this is an axial point. Okay, so you just find the electric field for this dipole and electric field due to this dipole at this point. Okay, and then vectorially add it. Okay, you'll get your answer. Okay, so let's consider the electric field due to this dipole. Okay, so electric field 1, we'll call it, that will be, this is equatorial point, right? And the field at equatorial point is kp by r cube minus kp by r cube. Okay, so the direction of the electric field over here due to this dipole will be opposite to the dipole moment, right? It will be along minus k cap. Okay, because dipole moment is along k cap, and the direction of the electric field due to a dipole at equatorial point is opposite to its dipole moment, right? So the dipole moment is along k cap. The electric field due to this dipole over here will be along minus k cap. Okay, and the magnitude will be kp by r cube. What is r over here? The distance from the center to this point, which is 1, right? So kp by 1, okay, 1 cube. So that will give you minus kp in the minus kp k cap direction. Okay, that is the electric field due to this dipole at this point. Now time to find the electric field at this point due to that dipole. Okay, so E2. Now this is an axial point. At axial point, the electric field is given as 2 kp by r cube, and the direction will be same as that of the dipole moment. Here I'll write p dash because the value of the dipole moment is p by 2. Okay, so here the direction for an axial point, the direction of the electric field at an axial point is same as the direction of the dipole moment. Okay, so you just have to use the direction factors and just expresses this vectorially and then add. Okay, and you'll reach your answer. Okay, so here E2 will be E2. So just substitute the values. 2 k, p is p by 2, dipole moment here is p by 2, r cube, what is the distance over here? It is 2, right? The distance over here is 2. Okay, so 2 cube, that will be 8. Okay, all the units were given in meters. Okay, don't worry about that. This and this will get cancelled, so you get kp by 8. And what will be the direction? K cap, right? Same direction as the direction of the dipole moment for an axial point. Okay, so you have E2 and you have E1. What do you have to do? You have to find E net, which will be nothing but E1 plus E2. Vectorially, you have to just add them, right? Now when you add them, this is E2, that is E1, right? So minus kp k cap plus kp by 8 k cap. What will that give you? That will give you minus 8 kp k cap plus kp k cap, that will be minus 7 kp k cap divided by 8. Right, now you can in place of that k, you can just put 1 upon 4 pi epsilon naught, right? This k is nothing but the constant 1 upon 4 pi epsilon naught. So you get minus 7 p k cap, and you have 1 upon 4 pi epsilon naught. 4 into 8 is 32. So 32 pi epsilon naught. 4 8s are 32. Okay, so option B is the correct choice over here. So net electric field at this point, we get it by adding the electric field vectors due to this dipole and that dipole. Okay, and the answer is minus 7 p k cap divided by 32 pi epsilon naught. Okay, yeah, so that is our answer. Let's move to the next question now. So question 13 over here. In this question you have two spherical shells, one with a radius RA and the second one with radius RB. The one with radius RA has a charge QA on it, the one with radius RB has a charge minus QB on it. Okay, it is also given that QB is greater than QA. You are supposed to find the correct plot of E versus R. Okay, so let's think through this one. So we'll consider region by region. Let's choose this region first. Okay, inside both the shells. Okay, inside shell B as well as inside shell A, this region. Okay, so the electric field in that region should be obviously zero, right? Electric field inside a spherical shell is zero. Okay, so you can see that it is inside both the shells, so the electric field at this point will be zero. Okay, and this is true for any point inside this shell RA. Okay, because it is inside that shell, right? So electric field till RA should be zero. Okay, A seems to be the correct option. Anyways, we have to go ahead and see the other ones too, but option B is incorrect, right? The electric field at RA should be zero. RA is not marked over here, we can't say anything here. This option C is incorrect. Okay, we can say it for sure because till RA the field should be equal to 0. Okay, field in this region is 0. Inside the conductor, inside the spherical shell, this field the field is 0. Okay, it can be none as well. So let's see now over here. Okay, on the surface of your first spherical shell. Okay, we know that at the surface the field will be 1 upon 4 pi epsilon naught QA by RA square. Right, this will have some value, of course. So here you can see in option A it has some value here also, but this is already rejected. Right, now we have option A, B and D. Okay, so it will have some value, right, for EA. Okay, at this point it will have some value. Now what about this point? This point is a point between this two concentric shells, right? For this point, it is a point outside of this shell but inside of the bigger shell. This point is outside of the smaller shell but inside of the bigger shell. So due to the bigger shell, there will be no field on it because it is still inside the bigger shell, right? Field inside a shell is 0. So field due to the bigger shell on this one is 0. Okay, the only field on this one is due to the smaller spherical shell. Okay, and we know that the field outside a spherical shell is inversely proportional to 1 by r square. Okay, so for this region from the radius of A to the radius of B, in this region between them, okay, the field should vary this way. Okay, it should be inversely proportional to r square. Okay, here you can again see it in option A. Okay, and here I cannot make something out of that graph. Okay, anyways, I know it's wrong. Okay, so anyways, here in option A you can see that between RA to RB the field is inversely proportional. It satisfies this one. Okay, now let's see what happens at the surface of B. Okay, at the surface of B you can see that there will be field due to this spherical shell. First of all, QB, right, it will be K QB, it will be minus this time, right, minus sign. The field will be inside, you can see that, and divided by RB square. And also the field will be due to this spherical shell, right, because that point is a point outside the smaller spherical shell. Okay, I hope you are getting my point. You can rewind anytime you are confused, you can rewind and watch the video again. Okay, so here the point is outside this spherical shell, so this point will experience a electric field due to the smaller shell as well. Okay, as well as it will experience field due to the bigger shell as well as the smaller shell. Okay, and due to smaller shell the field will be KQA by this distance square, right? This distance is RB square. Right, now just add this to, we have to find the electric field, net electric field over here. Okay, so you can see that Q will be minus KQB by RB square and plus k q a by r b square. Okay, so k by r b square is common, right? K by r b square is common. I'll write it somewhere else. K by r b square is common. Okay, this might seem tedious, but it is, trust me, it is very easy. Okay, so k by rb square is common, and here we are left with minus qb, right? Minus qb, and there we have plus qa. Now you can see that qb is bigger than qa, right? qb is bigger than qa, so this value will be something negative. So e net is coming to be something negative over here, right? So E net over here at RB is something negative. Okay, so graph A satisfies that as well, even graph B satisfies, but anyways we'll prove it for graph A, and we'll find that the graph A is the most appropriate explanation over here. I think there is an error in graph B over here because RA is not marked over there. Okay, anyways we are left with the final part, and the final region is over here, okay, which is outside both the shells. Outside both the shells, you can just treat the two charges to be concentrated at the center. Okay, you can just take the two charges at point charges at the center, right? And you can see that at outside the region, the charge will be inversely proportional to r square. So again, you can see the inverse relation over there. So option A is the correct graph over here. Okay, I'll just sum up the process. We just divided the process into four regions. Okay, 1, 2, 3, 4 and 5. Okay, so 1 is inside both the spherical shell, where this field should be 0, right? It's inside both the shells. 1 at B, which has a specific value, 1 at A, okay, RA, 1 at RA, which has specific value over here, right? Some specific value positive in need. And now the 1, 2. Now third one is between these two, between the first spherical shell and the second spherical shell. Between these two, due to the second one, there is no electric field, right? Because the point is still inside, and here the field due to this one, due to the small one, the point is outside, right? Outside, for outside, it's inversely proportional to r square. So again here inverse relation you can see at RB. At RB you can see that we found the net field. Now it will be due to both, right? Due to this one, due to because the point is on its surface, and now this is outside, right? This point is outside. So then we found out the net field to be negative. So net field is negative and has some specific value over there, right? And then again we took it to the next region, which was outside both the shells. Now outside both the shells, of course the relation will be inversely proportional to r square. So again you can see that relation. So option A is the correct choice over here. I think there is some error in B, just forget about it. Let's move to the next question now. So question 14 over here, now from the moderate category. Congratulations if you made it this far. Now in this question you are given a charge distribution. You are supposed to find the dipole moment of this charge distribution. Okay, so it is a good one. You can pause this video now and give this question a humble try. Okay, so first of all you can see that it is a slightly tricky question, right? Suppose we had two discrete charges plus q and minus q, which are separated by a specific distance. Then we know that the dipole moment of that system is simply given as the magnitude of charge into the distance of separation, right? But here the distribution is uniform, right? Here a charge distribution is given. We don't have two discrete charge. Plus q is distributed over this side of the quadrant, right? This side of the semicircle, and minus q is distributed over this side of the semicircle. Okay, now in this case we have to use a little bit of integration. Okay, so let's do it. So first of all I'll make an angle theta with the horizontal and cut an element dx over there. Okay, this element has a length dx. Okay, and let's suppose the charge of that element is plus dq. Okay, and that it subtends an angle d theta over here. Similarly, I'll choose one more element over here of length dx, which has an charge of which has a charge of minus dq, okay, because we are considering dipole moment over here, right? So let's select a pair, it's pair over here. So similarly I'll make an angle theta over here, and I'll cut out an element which has length dx. The charge on this one will be minus dq, and the angle subtended by it over here will be d theta. Okay, so we have to find the dipole moment. Can I write the dipole moment over here as the small dipole moment due to these two charges? First of all, I'll write that and then integrate. Okay, the steps are clear. So dipole moment due to these two charges over here will be the magnitude of charge dq into the distance of separation. So the separation distance is over here, right? So this distance d. So you can see that d will be nothing but, okay, you can draw, this is nothing but radius, right? This is nothing but the radius of the semicircle. This is r, this is r. Okay, this r was given in the question as the radius of semicircle. Okay, so this distance is r, this is r. Okay, so you can see that this distance from here till here will be nothing but r cos theta, right? R, here the distance will be nothing but, this distance will be nothing but r cos theta, right? Adjacent to theta is r cos theta. Similarly over here, the distance over here will be nothing but r cos theta. Okay, so you can see that this d is nothing but r cos theta plus r cos theta. I hope that is clear. I just got the cos component of this, so you can see that if you add this two, you get the distance d, which is the distance of separation. Okay, so r cos theta plus r cos theta equals d, right? R cos theta plus r cos theta is equal to that distance of separation. So dq into the distance of separation d, which is nothing but 2r cos theta. Okay, the distance of separation is 2r cos theta. Okay, you can see that. Now how to find this dq? To find this dq, we have to use a little bit of logic of your charge density. Okay, so we can define charge density lambda as dq by the length of that element, dq, the charge of that element divided by the length of that element. Okay, and if you see, lambda can be written in one more way, which is we can write it for the surface, right? For this quadrant entirely we can write it. So in that case, lambda will be charge on that length, which is nothing but, here the charges over this entire quadrant, the charges plus q, right? Plus q is distributed over here. So the charge over here is q divided by this length. Okay, lambda is basically the ratio of charge by length. Okay, charge of a particular element to the length. Okay, so here the charge is plus q and it's distributed over this quadrant, right? This quadrant corresponds to 2 pi r, 1/4 of 2 pi r, right? This is 1/4 of the entire circle, right? If you complete the circle, this is 1/4 of the entire circle. So this distance is nothing but 1/4 of 2 pi r. So this and this will get cancelled. Here you'll get 2. So you can write lambda as this 2 will go on top, 2q by pi r. Okay, so you will get lambda as 2q by pi r. You can plug it over there. Okay, let's plug it over there. 2q by pi r gives you dq by dx. Okay, so you get what is dq by dx. So I'll express that dq in terms of dx. Okay, let me show you why. Then I can express that dx in terms of d theta. I'll show you. So this is pi r, right? Pi r. Okay, so 2q pi r into dx will give you dq, right? But here we want everything in terms of theta. Okay, we want dq in terms of theta. Okay, because theta is the variable over here, we don't want this dx. So we'll express dx in terms of this d theta. Okay, so we can do that. So easily we can see that d theta is the angle. So we can write this angle as length of the arc, which is dx by the radius. Right, we can write this angle d theta as length of the arc dx by the radius. So you can simply write dx as r d theta. Right, so in place of dx we can plug in r d theta. Okay, so let's plug in that value over there. We'll directly plug it over here and integrate. Okay, so 2q by r, 2q by pi r into dx is r d theta into 2r cos theta, 2r cos theta. Okay, now the only variable over here is theta. Okay, you can see that r and r will get cancelled. This r is the radius of the semicircle, constant, 2 is constant, q is the charge which is distributed, which is also constant, and pi is of course constant. Okay, so the only variable over here is this theta, right? We are varying this angle, choosing one element at each time. That is what integration is. Okay, so we are going to integrate this and we'll hopefully find the dipole moment over here. Okay, so are we good to go ahead? So where shall we do it? Do it over here. I'll erase this. You can note this down. Okay, pause and note if you want to. So I'll erase this off. Okay, so let's integrate it over there. So integration of dp will give us the dipole moment p. Okay, and now we have 4q by pi. So 4qr by pi, 4qr by pi, and cos theta, this everything is constant, that will come out of the integration sign. Okay, I hope you know that we have integrated it now. dp becomes p and we have integrated the right hand side too, and this is the variable, right? All this are constant. 4qr by pi is constant. Okay, now integration of cos theta. First of all, what are the limits? So you can see that we are going to vary theta from 0 degrees to 90 degrees, right? And in doing that, we'll account for all the pairs, right? If we vary theta from 0 degree to 90 degree, we'll account for all the pairs, right? Because for 1 theta, we choose one pair, right? So if we move theta from 0 degrees to 90 degrees, we'll account for all the pairs. Okay, so this limit of integration goes from 0 to pi by 2. Now integration of cos theta is sin theta. Okay, sin theta, and now you have to substitute the limits. So sin pi by 2 is nothing but 1. So the answer that you are going to get is dipole moment is 4qr by pi. Now this is the magnitude of your dipole moment. What about the direction now? Okay, so we have to consider the direction as well. First of all, you can see that option C and option D are incorrect. So either it's option A or option B, right? 4qr, 4rq by pi, 4rq by pi. Okay, so is it along positive I cap or is it along negative I cap? That is the question. So can you see that? Do tell me in the comment section, mention the time and tell me in the comment section. Okay, the correct answer over here is it is towards the positive x-axis direction. Okay, option B is the correct choice over here. It is along positive I cap. Why? Because dipole moment is from the negative charge to the positive charge. Here also you can see that for this two charges, this 2 point charges, dq, minus dq and plus dq, the dipole moment will be from the negative side to the positive side, right? The direction of the dipole moment is towards the positive x-axis. Okay, so this is the correct answer over here. Let's move to the next question now. I hope this is clear. You can surely rewind the video and watch this again if you are confused at some parts. Okay, so let's move to the next question. So question 15 over here, this is your homework question. You can pause and take a screenshot if you wish to try it later. Okay, so actually I was supposed to do this question in class today, but the time's up already. Okay, this is a lengthy lecture now, so I won't do it in this class. Anyways, I'll make the text solution of this question available on the website, so you can go and check it out over there. Okay, so that's all for today's class. I hope you enjoyed it. If you did enjoy it, smash like, subscribe. I'll see you soon in the next class. Keep enjoying physics.